Hello everyone, today we will have lecture 36 and we will continue our discussion on. So, the topic is oxidation of metals and alloys. In the last lecture what we have seen different stages of oxidation of a metal when the metal is in contact with oxygen at a high temperature, and we have seen mainly there are 5 stages starting with adsorption of oxygen, followed by nucleation of oxide on the surface, as well as dissolution of oxygen in the form of solid solution or liquid solution in the metal. The solid solution or liquid solution, I mean to say that when the metal is in solid state, then it is solid solution. When it is liquid state, it is a liquid solution of metal and oxygen. And this dissolution of oxygen in the form of solid solution or liquid solution, that could lead to internal oxidation. And then we have a film of oxide on top of metal, and that film can generate cracks, that could be micro cracks or macro cracks, even there could be porosity, and there could be also spallation, that means the oxide can spall off from the surface of the metal, because oxides can have a different thermal expansion coefficient, as well as there could be a problem of a differential volume change. And when we started talking about differential volume change, we talked about peeling bed work ratio, and this ratio is designed on the basis of whether the metal oxide that forms on the metal surface covers the entire surface or not. If it covers, then we would say that it provides protection to further oxidation, and if it does not, then it will not give protection. But in the case where it covers, if it is too much of oxide volume from the oxidation of 1 mole of metal, then that case there could be a possibility of fracture of metal oxide, which might lead to formation of macro cracks or micro cracks, or even spallation of oxide from the surface, leading to exposure of metal surface to the oxygen again. So, that case it will not be able to provide much of oxidation resistance. So, if we talk about peeling bed work ratio, so this is a ratio between molecular weight oxide divided by density oxide, and that is to be divided by atomic weight of metal of 1 mole. This is very important, and now we will do some numerical problem, and there it will be clear that why this 1 mole is important, divided by density of oxide. And there and this is shortly called as PBR. Now, we also notice that if PBR is less than 1, no protection, PBR greater than 1, but 1.5 to 2, it gives protection, and PBR greater than 1.5 or 2, then less protection. In all those 3 cases, if we notice carefully, that only it considers that what is the volume of oxide that generates because of oxidation of 1 mole of metal. But it does not consider several other things which are very important. We will see one by one, and few examples, classic examples we will see. Now, at least if we go by this PBR, let us do some calculations. Let us do a calculation for aluminium. In case of aluminium, molecular weight of Al2O3 is equal to 10196 gram, atomic weight of aluminium 26.98 gram, rho the density of Al2O3 equal to 3.89 gram per centimeter cube, and density of aluminium 2.7 gram per centimeter cube. Now, since we are considering that here it will, when aluminium is oxidized, it forms Al2O3. So, we have to write the chemical this reaction Al plus 3O2 to Al2O3. So, this is the balanced equation. Now, if we see that we have to consider 1 mole of metal which is getting oxidized. So, if we convert it into 1 mole, so it would be so now we have to consider molecular weight and density of the oxide of half mole of Al2O3, since 1 mole of metal aluminium gives rise to half a mole of Al2O3. Now, interestingly, if you see this particular thing, these are indicating the volume of the metal of 1 mole, and here it is the volume of oxide which is generating from 1 mole of metal oxidation. So, if we try to calculate PBR, it will be equal to 10196 divided by 89 . So, this will be 1.30, around 1.30. So, if we see this particular value, this particular value lies in this range. So, we can say that it gives you protection to oxidation. And in fact, Al2O3 is a very good example which gives a very good protection to aluminium, since it forms a thin layer on top of aluminium, and since the volume of Al2O3 that is generating from 1 mole of metal oxidation is sufficient to cover the entire surface. So, that means we have a barrier. So, that means here initially it was metal, aluminium and oxygen. Now, we have a barrier, thin barrier of metal oxide, aluminium. So, this condition is a very favorable, very much favorable condition for giving oxidation resistance, because oxygen does not have a direct contact with aluminium, rather oxygen has to somehow reach out to the aluminium surface through the metal oxide, and that reaching out of oxygen is a complex process. It involves diffusion. So, we will talk about that diffusion little later, but at least oxygen access to the metal will be difficult, and that is what it will have resistance to oxidation. So, this is one example. We can do several such examples in case of chromium, and chromium, in case of chromium, if we take the chromium data, you will see that PBr ratio will come out to be around 2, which is also good. Even for FeO, it will come out to be 1.76. It is also good, but what I mean to say now here, this 1 mole is important, because in this case it becomes half. Let us say for FeO, the reaction would be Fe plus O2 equal to FeO. So, this is the reaction. That case 1 mole generates 1 mole of FeO. So, that time this factor will be 1. Now, similarly, in some cases, for example, Si plus O2 equal to SiO2, that case still it is 1 mole and this factor would be 1. So, all those cases PBr ratio becomes very straightforward, and that time only we have to consider molar volume of that oxide and molar volume of the metal. But in case of aluminium, in case of chromium, wherever we have, in case of chromium Cr2O3 forms. So, there we have to consider this factor, there will be a factor which will be not equal to 1. So, that factor would be very critical to find out PBr. Now, you can calculate for other cases, some of the metals where PBr ratio is less than 1, let me note it down. For example, if you take magnesium, so that time if I try to put down all those values, magnesium is 0.81, and that time oxide is MgO. Then calcium, so that time oxide is calcium oxide, it will be 0.64. Of course, we have seen aluminium and oxide is Al2O3, PBr ratio is 1.3. Then we can also find out PBr ratio of iron, Fe, oxide is FeO, PBr ratio is 1.78. Now, if you take Al2 Fe2O3, PBr ratio would be different. In case of Fe2O3, the PBr ratio would be, when this is iron, but oxide is Fe, it is Fe2O3, that time PBr would be 2.14. So, these are the oxides which are protective, and if you see one factor, in case of FeO it is 1.78, but Fe2O3 it is 2.14, though it is little more than 2.14, but Fe2O3 is very much protective for further oxidation of iron. Then we have some oxides with much higher value, for example, molybdenum, where oxide is MoO3, its PBr is 3.27. But in this case, of course, I will not expect that much of oxidation resistance as per the PBr fundamentals. Then chromium, where oxide is Cr2O3, that time PBr becomes 2.02. Now, interestingly, so that way you can calculate PBr once you know the oxide form, then you need to know molecular weight of that oxide, density of that oxide, as well as metal atomic weight and metal density. And from the reaction, the balance reaction, we have to find out 1 mole of metal is getting oxidized and forming how many moles of metal oxide, and that way you can find out. Now, interestingly, this gives an idea. For example, here I can definitely say that it is not covering the entire surface. So, it will be exposed to the oxygen all the time. I would expect that we would expect that it will oxidize continuously and at a very high rate. But in this case I can consider that this is protective. This case I can say that it is not protective, because once we have a very high volume, now if let us say the metal, oxygen and metal, so that is getting oxidized, this is the oxide layer, and now this oxide layer has got a very high molar volume, and since oxides are brittle, so further growth of that oxide would lead to a stress on the particular metal surface. This stressed because of the further metal oxide formation, and this stress can lead to cracking on the oxide surface if the molar volume becomes very high, and then once it cracks, definitely it will not be able to protect it. Chromium also, it is a protective oxide, and that is what we use chromium in stainless steel, and its PBr ratio is little more than 2, but still we can consider it to be protective. Now, interestingly, if you see that, we have seen that the value, if it is 1 to 1.5 to 2, then we can say that it is protective, but in this case it is little more than 2, but still we say that it is protective because it is close to 2. So, that means it will not provide much of stress on the metal oxide layer when further oxidation takes place or during the oxide growth stage. But here also the same story, but here as per the PBr we would say that this is not protective. Now, interesting story comes when we talk about PBr ratio of zirconium oxide or zirconium. So, where PBr ratio is in case of zirconium is 1.57, sorry. So, this oxide is ZrO2, PBr ratio is 1.57. Now, here we say that it is protective, very much protective, and of course, it is protective, but zirconium has a peculiarity. If zirconia is heated, there will be phase transformation, and this phase transformation leads to problem. So, for example, if I consider the zirconia phase transformation, this is called zirconia ZrO2, the room temperature phase is monoclinic, which has an allotropic transformation to tetragonal, and then again at 2640 K it goes to cubic phase. When it goes to and if I try to see the density of the metal oxide, it is here, it is 5.83. This is density of ZrO2. Here it is 6.10, and here it is 6.09, and density, the unit if I consider gram per centimeter cube. Now, interestingly, if you see that if the density is low, that means it has a higher molar volume. If density is low. If density is low, then it will have a higher molar volume, and vice versa. That means, if the density is more, molar volume would be less of that oxide. Now, you could see that when it goes from monoclinic to tetragonal, we have volume contraction. Again, from here to there, I have volume expansion. But interestingly, zirconia use is at a high temperature. Now, if at high temperature we are using that zirconia in the form of tiles or something at a high temperature heat resistant material, so there it will have a cubic structure, and once it is cooled from this to monoclinic, I will have volume expansion. And these volume expansion would lead to crack formation, and once the crack forms, then the oxide will try to break off. Now, even if zirconia is protective, still I could see that as per the PBR ratio, I could see that this volume expansion due to, or volume expansion or volume contraction due to change in structure, we are not considering. So, that means PBR does not consider phase change of the oxide. Fine. So, since it is not considering phase change, it is not going to tell us the actual picture, the way it is happening in case of zirconia, that high temperature phase will not be stable at room temperature, low temperature, and that time cubic to monoclinic transformation would lead to volume expansion, and that would create crack in the zirconia. Now, of course, if you add yttrium or magnesium or calcium to that zirconia, it tries to stabilize cubic phase at a room temperature. So, that is what we avoid, that phase transformation, and that would lead to a stability in the zirconia, that crack formation would not happen because of the volume expansion in the oxide layer, and that is what we use zirconia, yttria stabilized zirconia, which stabilizes high temperature phase down to room temperature. But from the PBR aspect, it does not consider this phenomena. Like that, PBR does not consider many other things, like let us note down all those factors what PBR does not consider. Volume change due to phase transformation. since it only bothers about the volume of the oxide and the volume of the metal, it does not consider the phase change or allotropic transformation in the metal in that oxide. Second part, now in order to, for example, in case of one metal, PBr ratio is around 1.5, but if that oxide has a low vaporization temperature, then that would lead to a problem. So, that problem can be, for example, even if it is having very favorable PBr, but at high temperature it will vaporize, because it has a very high vapor pressure, since its boiling point is low. That is also not considered in case of PBr. So, oxide should possess very low vapor pressure, or I could say that it should have, oxide should have high melting as well as boiling temperature. This is not considered in case of PBr. The classic example is silicon oxide and these two oxides. So, when we talk about silicon oxide, then let us calculate the PBr for both the cases. In case of silicon oxide, the data, if I consider FiSiO2 equal to 60.08 gram per mole, rho equal to 2.65 Tm equal to 1713 degrees Celsius, T boiling 2950 degrees Celsius. And here SiO, this is 44.08 gram per mole, 2.13 Tm equal to 1702 degrees Celsius, but Tb, which is the boiling temperature, is 1880 degrees Celsius. Now, if I try to calculate PBr from a silicon data, this is atomic weight of silicon is 28.08 gram per mole. Then we have rho is 2.33 millimeter cube. So, here PBr for the reaction silicon plus O2 equal to SiO2 would be 1.88, and here PBr would be equal to, the reaction would be, it will be 1.717. So, now I could see that the PBr in both the cases, it is closely lying, but interestingly, because this has boiling point 1880 degrees Celsius and here the silicon oxide is 2950 degrees Celsius. So, this one would try to evaporate, and once it evaporates, there will be no oxide layer sticking to the surface and it will expose the metal surface for further oxidation. So, these particular factors are not considered in PBr. So, there are other factors like, for a oxide to be protective, it should be very compact, and adherent, third, fourth, it should have matching expansion coefficient, or I would say thermal expansion coefficient. Then it means oxide. So, it should have a low diffusivity of ions, and here I am considering O2 minus and metal 2 plus, or I can even consider metal N plus. For example, in case of aluminium it will be Al3 plus, in case of chromium it is Cr3 plus, whereas in case of iron it could be either Fe2 plus or Fe3 plus. So, these ions would have a very low diffusivity, that means the defect concentration in the metal oxide would be less, should be less. Okay. So, these factors are not considered in the PBR ratio. So, that is what the PBR ratio can give you an indication that some oxide could be protective or not, but that will not be definite. So, in order to have a definite approach, one has to study the oxide layer, its other characteristics like the defect concentration in the oxide, like what is the melting point, boiling point, what could be the thermal expansion coefficient, and whether it is adherent or not, whether it is compact or not. So, those factors we have to study, we have to understand one by one. But for our understanding, we will look at this particular issue in a little greater detail, and rest of the thing we will not touch for the time being, but this factor, the diffusivity of ions factor, will consider, that will explain us which surface would grow, whether metal oxide interface would have oxide formation or oxide oxygen interface would have oxide formation. That can be told if we know the defect information in the oxide as well as the diffusivity information in the oxide. So, let me stop here. We will continue our discussion on the oxidation of metals and alloys in subsequent lectures. Thank you very much.